we're going to go thermochemistry day 3. We're going to talk about thermochemical equations. And in this one, we're going to be talking about thermochemical equations and how to use this to calculate energy in a chemical reaction. We're going to explain what the delta H of a reaction is and how can it be found. So a thermochemical equation is a chemical equation which includes the energy used used or produced in a chemical reaction. So energy reactions usually are going to have an energy change associated with that. So I want you to think of it as a regular equation, but we're going to add some sort of heat change in it. So let's give you an example. Enthalpy. The word enthalpy is the heat content of a substance at constant pressure. So what I want you to think about is this term called enthalpy and how it kind of relates to heat. This is called the heat of reaction, or the heat that's absorbed or released during a chemical reaction. Now this is very important because heat is generally going to be released or absorbed depending upon the reaction that you're driving. And so we're going to denote this as delta H, or change in enthalpy. And this is going to be a very important concept because it's going to tell us how much of that heat is moving in and out of an object. So let's give you an example of an exothermic. An exothermic reaction can be written as this way. CH4 plus 2O2 gives you CO2 plus 2H2O. And our delta H here is negative 890.4 kilojoules. So in this example, it's an exothermic reaction. This is releasing heat because you're negative delta H. The negative signs means an exothermic reaction. If it's positive, it's going to be endothermic. So if I take a look at this reaction here, it's going to say plus 890, which means it's an endothermic reaction. And it also, you can write it on the product side. So if the product is written here, it can also be exo. Here, I kind of made a mistake earlier, but if it's written on the product side, it will be considered exo as well. So treat the heats as another product or reactant. Now for the endothermic, let's talk about this way. Endothermic means that I need to put energy in. So in this example, I'm putting 89.3 kilojoules to the reactant side, and the positive sign means it's endothermic. So for example, if I put 89.3 right here, I'm saying that I'm applying energy to move this reaction forward. And that's going to be basically applying some heat using a Bunsen burner or using some sort of flame to actually start this reaction. This reaction is an endothermic because I'm putting it on the left-hand side. So the heat of reaction is the amount of energy used or produced when the coefficient equals the number of moles in a reaction. So we want to talk about this in terms of moles, or the coefficient. And generally the coefficient of any substance is equal to delta H. So this is called our new conversion factor. And I'm going to be going ahead and explaining that here in just a bit. So here's a couple examples. How much energy is needed when 1.27 moles of sulfur react with excess carbon? So in this example, it's an endothermic reaction because I have 89.3. So I'm going to take 1.7 moles of sulfur, and I don't know the units of energy. So what I'm going to do is look at sulfur, which is a 2. I'm going to use 89.3, and I'm going to convert this into energy. So it's going to be 2 moles of sulfur times 89.3, cancel, which gives us 56.7 kilojoules of energy. Simple as that. So all we have to do is divide by that coefficient to get to the kilojoules of moles. Now it says here it's needed, so that means I need to add 56.7. Okay. All right, let's go ahead and pause the video and see if you can do the next one. How many moles of water would be produced if this reaction gave off 347.1 kilojoules of energy? Now it says gave off. So what that means is you have to kind of think about what that means here. So CH4 plus 2O plus CO2 gives you 890. So now we're going to do is put negative 347 kilojoules because it's negative, because it's given off, gave off. Then we're going to do the moles of H2O. And now we're going to do is take 2 moles of H2O to 890, and we're going to set this up as negative 347.1 kilojoules divided by 890. But now because we're using water, we're going to use a 2. And in this example, we're going to multiply 2 times negative 347. We're also going to use our negative value because this is on the product side. And we're going to cancel this, and we get 0.7796 moles of water. Okay, so make sure you pause this video to understand how this works, but it's very important to understand that this is actually a kilojoules situation. Okay. All right, let's take a look at the next one. How much energy required is produced when 0.75 grams of oxygen reacts with excess ethanol? So in this example, we have a product side of 1235 kilojoules, which means that it's given off. It's an exothermic reaction. We're going to write 75.0 kilograms per O2. We also don't know how many kilojoules we have, so what we're going to do is take a look at oxygen, and we look at 1235 kilojoules. So now we're going to take 75. We're going to use 32 over 1 mole because that's going to be our conversion factor for molar mass. Cancel, cancel. We're going to use 3 moles of this, which is going to give us negative 1235. So again, we're going to use that negative number. Cancel, cancel. And now it's going to be negative 965 kilojoules. Okay, so that's going to be our final answer because that's 965 to 1235. Okay. Now it says here produce, so we're going to use an exothermic reaction for that. Okay, if you have any questions, turn on to worksheet 3.